Hello, Precalculus student. This video is for chapter 4.1, part 3. We are still in the process of finding exponential function, given some information. So earlier we were given some rate and also the initial value. Now we are given not the rate at all, but just two instances. So for example, a car was bought at year 2010 for $25,000. The value depreciated to $13,050 in year 2014. So 4 years. So we can say at 2010 is t equal to 0, 2014 is t equal to 4, and y would be equal to 25,000, and this is the y at this time. So you can write down the two values just like when we write down 2.0 is 25,000. So we can tell this is A, right? And then we have 4 is 13,050. So write the equation. So we will need to find y equal to abx, right? So y equal to abx, y would be first, would be 25,000 equal to ab0. That means 25,000 is A. And so that's the first equation. The second equation is y equal to 1350 equal to A. Well, our A is 25,000, but let's just write it there. And B, we don't know, to the power 4. So I want to solve for B, so I want to isolate B to the 4. So B to the 4 would be 13,050 over 25,000, right? And then to solve for B, I do the fourth root. Again, if you have to use decimal to do it, you do to the power 1/4, okay? 25,000. So that would equal to 0.85, right? So the model would be y is equal to 25,000 times 0.85 to the power t, okay? If the value continues to drop by the same percentage, what percentage does it drop? It dropped 15%, right? 1 minus 0.15 is 0.85. The factor is 0.85. The rate of drop is 15%. The same drop. What's the value at 2020? T would be what? 2020 minus in the beginning is 2010. So T is 10. So we just plug in the formula. Y equal to 25,000 to the power, to the base of 0.85, 10. So 25,000, 0.85 to the power 10. 25000 times 0.85 to the power 10. That will be 4921. 0.86. And you can check that it's 14. So it was, if you check to the power 4, it is 13050. So this is the right answer. So this is how you can use some statement about the rate. You can use some 2-point to find a function. The other application of exponential function is it can be used to model compound interest, because compound interest is concerning the saving where the interests are when the interests are credited to the account, the interest also can earn interest. So it's like there is a constant percentage increase, right? If the bank gives you a constant rate, then whatever that you have a constant rate. So it is modeled by exponential function. And because the growth is not like the compounding is not constant, so there is this formula called A of t, which is the amount in the account, equal to P, principal, the initial value, with 1 plus not R, but R over N, where N is the compounding period in 1 year. So how many times do you compound, or how many times do you receive the interest per year? over n and n times t. So this is the general compound interest formula. If you get the interest more frequently, you would compound more frequently, but each compounding period you will get less interest rate. So the b would be 1 plus r over n, but then the exponent will be not just t, where t is year. T is measured in years, always in year, and rate is given as the annual percentage rate, so it's always NT. So let's use this formula. There is an initial investment of 100,000 and the rate given is 12%. If the compounding is monthly, what will be the investment in 20 years? So if we are compounding monthly, every year we will have 12 times of compound interest being accredited. So we compound 12 times per year. So the A would equal to, if you look at the formula, it would be equal to, this is the initial investment, so that is P, and this is R, right? And T is 20. So we have to, you can see this formula is quite complex. You have to plug in P, you have to plug in R, you have to plug in N, you plug in T. The only thing that usually they give you P, R, and T, but N, which is number of compounding per year, you have to figure it out by looking at how frequently do they compound in 1 year. So in our case, it would be 100,000, 100,000. 1 plus R is 12%, change it into a decimal, 0.12, over N is 12, and then NT, so 12 times 20. So that means you put in the calculator all in one shot. So let's see, I'll try to put it in decimal. So in case you want 100,000 times 1 plus 0.12 over 12, right, to the power up arrow. You have to do the up arrow at shift 6, 20 times 12. Oopsie. 20 times, I think I have to parenthesis it, 20 times 12 like that. So it's in the exponent. Okay. So it's 1089,255,36. Oh, can I remember? 1089,255 point what? 3737 dollar. Okay. But if the compounding is quarterly, that means they are less frequent. What will be the amount in 20 years? So that should be less, right? Wow, just imagine you start with 100,000 and then after 20 you have 1 million. So 100,000 again. Because quarterly, every year I only have 4 times of compound interest. So 0.12, but I divide it by 4. And in the exponent, I do 4 times 20, right? NT. So put in the calculator, you can just change this to divided by 4. And then instead of times 12 is times 4. So 1064089.06. So 1,064,089.06 dollars will be 20 years. So this is another examples about compound interest. The student want to save 40,000. That means he or she wants to have this amount in 3 years. So T is this, but this is the final account amount that he or she wanted it to be. She invests in an account that pays 6%, so this R, but it's not 0.6, 0.06. Compound semi-annually. That means every year you only get 2 interest, so n is equal to 2. How much will the student invest now? That means what is p, right? So we would write this, use this equation a equal to p 1 plus r over n and t. So let's figure it out. So we know the answer a, 40,000. No, yeah, 40,000. P we don't know. We don't want how much to save now. If I know the interest divided by 2, because it's twice a year, and 2 times 3, want it in 3 years, 2 times 3 here. So I want to find P, so I would just divide this whole group on the other side. So P is equal to 40,000 over 1 plus 0.06 divided by 2 to the power 2 times 3 is 6. So put in the calculator. We can do 40,000. Instead of multiply, is divide, right? So divide, can I, 1 plus 0.06 divided by 2, right? To the power 6 here, to the power 6. So 33499.37. So P equal to 33499.37. So you can see that it is exponential function is very useful. Now, ABX model is just one model. It is easy to use, easy to understand, because we know that B is what you get or what you multiply every period. There is another model that can be used to model continuous growth. So these are growing every period. Every t equal to 1, t equal to 2, you times a constant number. What happens if the growth is continuous, that's so finite, like every second, every half of a second, you get more and more. So if I do 1 plus r over n, where n is like 1 million, or I grow very close, very, very fast, so that I get the interest, less than 1 second. So when n increase without bound, you can put in the calculator of 1 plus 1 over 1 million, but to the million time, the value is would approximate to a number called E. Okay, it's E. So now this number is an irrational number. It doesn't stop the decimal, and it's similar to pi. It never ends. Like the decimal place never ends. So it's not a fraction. So how do I can use this to model continuous growth, because it's as if for money you are getting the interest every single time. So if you use that, it turns out that the formula become A equal to A, the initial value, P, E of RT. So this is actually P, okay? E to the RT. For money, it's principal. For population or anything, it is A, E to the RT. R is the rate, but this rate is called a continuous rate, instead of just the constant rate. So the constant rate that you use for B is 1 plus R equal to B, but this is the continuous rate. If R is positive, then it is a growth. If R is negative, it's a decay, and is written as AE to the RT. So there is no 1 plus or 1 minus. You just look at whether R itself is positive or negative. For example, I have 1.34 e to the negative 1.2 t. This means decay, because this is k. I look at the base is e. If the base is e, I would look at, and then I would have a k. In front of the t, this number is the continuous growth or decay rate. The second one, the first number is the initial value, and it's e. I would look at the k or the r here. So this is k or r, which is the continuous rate. So the continuous rate is positive. This is a growth. Okay. And yeah, for business application, the A itself is the initial investment. So we get PE to the RT is called continuous compounding, and you can use it to calculate what you have for continuous compounding. So I'm going to talk about how to calculate the amount for continuous compounding or continuous decay in the next video.